I'm glad to welcome Professor Martin Ferus again. I think you were here 2 weeks ago or 3 weeks ago, because he is also a cooperator in our Venus project with Peter Voigt and myself. And Prof. Heyrovský Institute of Physical Chemistry. Difficult for me to spell, and he's the head of the spectroscopy department and an expert in experimental astrochemistry, you can say, laser physics, and he and his colleagues focus also on experiments and theory, but also experiments with lasers, and so where they try to simulate chemistry, atmospheric chemistry in the lab, or mimicking meteoroid impacts where plasma forms around and then changes the atmospheric composition. And he's also an expert or is involved in projects, in the ESA projects like Ariel, and also in Vision, with brought us together with Venus, and in several other projects. So I would say you give us today some kind of overview also, I understood, from your institute and research related to the plasmas in the test tube. So you see now how we know how life originated on Earth. So the floor is yours.
Thank you for introducing me. And yes, I prepared a kind of pell-mell of results regarding the exploration of physics and chemistry in relation to origin of life, or rather origin of prebiotic molecules, and also transformation of atmospheres, especially with the special focus on early atmosphere of Earth or other terrestrial planets. And our motivation is this. I think you well know this diagram showing that most impact craters on Moon are pretty old, and they are consistent with or their number and age is consistent with the era of so-called heavy bombardment taking place on Moon, but also on Earth and other inner planets during a few 100 million years of their evolution. And of course, if you somehow think in terms of Hollywood catastrophic movies like Armageddon, what does it mean, large impact or elevated impact flux? We imagine a catastrophe, or most of us imagine a catastrophe. But is it a catastrophe at all? Isn't it something very important for evolution of early planets and for shaping the environment of Earth as we know it, with water, oceans, air, and possibly also life on surface of Earth. This is, by the way, pretty old issue of Der Spiegel. It was after the first elections, not now. So, is it really a catastrophe? I would like to show you our results, and also by introduction also the state-of-art results, that impacts shouldn't be understood as catastrophic events, but crucial events which shaped the Earth, our Earth as it is. First, who published a very complex work focused on importance of impacts to evolution of early environment. Was nobody less than famous Carl Edward Sagan, who published in Nature this very interesting paper in 1992, and he quantified and also demonstrated theoretically that first of all, impacts had potential to deliver a lot of substances to early Earth, among them also organic substances. So they contributed very likely to early evolution of let's say, organic matter or organic chemistry on Earth. Second, not less important contribution of impacts according to his calculations was also energy delivered to Earth for chemical transformation of chemicals presented in the environment, because impacts create a plasma, they create hotspots on the surface, and this provides not negligible amount of energy for early planetary chemistry. So they have to be, it has to be counted also with impacts if we estimate energy like UV for transformation or chemistry of early environment. But also regarding the contribution of impacts to Earth as we know it now, the important is delivery of water and volatile substances. I think that you also know this diagram showing the pH2 ratio of terrestrial water is really similar to the H2 ratio of water discovered in asteroids. So it means that, or it's a clue that terrestrial water comes from impacts of asteroids, and the inner planets belong to so-called water delivery zone. So they have been dry probably in the beginning, but then impacts transported water and other volatiles to Earth. Regarding organic substances, this is very interesting diagram from this paper published by Jan and his colleagues in 2014, and they examined the oxidation state of old zircons, and there is very nice shape. Very interesting shape of this curve, showing that the early environment prior to 4 billion years ago was very close to reducing conditions. Of course, we don't know about the composition and the degree of how originally the early environment was reduced, but it was definitely more reducing than nowadays. And qualitatively, it is interesting that if you sketch also this curve of decreasing impact flux to Earth, these two curves are in very nice agreement. So when impact rate is decreasing, the oxidation state of early Earth is increasing. Very interesting trend, in my opinion. So this is about the exogenous delivery of water and volatiles and organic substances. Heavy bombardment belongs to era of very special era in history of Earth. Actually, I would like to highlight that between, let's say, condensation of water to ocean, sometimes somehow 4.3 billion years ago, and the first real fossil evidences, there is a gap of knowledge. We have only indirect knowledge or indirect evidences on how was this crucial era like on Earth, what was the environment on Earth. And it was era also of origin of life and shaping chemically the Earth as it is and as it was later. What we have are models, some indirect evidences like ancient zircons, maybe some meteorites, maybe in future somebody will also discover meteorites injected from surface of Earth to Moon in future, but who knows? Yeah, but definitely now we have really lack of knowledge. What we can do is also some, let's say, laboratory models, like, for example, laser interaction experiments we do. If I would summarize what impact mean to chemistry and early evolution of so-called pale orange dot, how we can call Earth, for example, based on the work of this lady who calculated the transition spectra or assumed transition spectra of such early planet rich in organic hazes with some methane in its atmosphere, so it should look orange, not blue. We can ask several questions. For example, if early bombardment is common scenario for evolution of all the rocky worlds, which is open question, we can assume yes, but some scientists believe that it's not common scenario of early evolution of rocky planets. And in such a case, if they are crucial for prebiotic evolution, then it could be also, let's say, some problem to habitability or create problem in evaluation of habitability of other planets which did not undergo heavy bombardment. What is also chemical influence on early planetary environment, and if they represent an essence or if they have some contribution to origin of life, or rather origin of prebiotic substances on early planets. We can distinguish, or I have tried to outline distinguishing of their effects of impact to global and local, because depending on size of impactor, we can really distinguish. And regarding the physical conditions, impact influence the surface relief, because they are creating very special sites, spots on planetary surface, impact craters filled with water and presenting heat and some hydrothermal activity, like Gale impact crater on Mars. So very special environment. I will show you that maybe these environments were some kind of niche, very favorable for prebiotic processes or prebiotic synthesis. They also caused atmosphere depletion. I will show you another experimental results showing that there is, for example, depletion of xenon-argon ratio, and it was very likely caused by impact. We performed some experiments and calculations in collaboration with my colleagues from Cambridge. And these experiments have shown that there is a really very nice influence on this noble gases ratio, because they can be ejected and ionized by impact. Also, there is influence on surface temperature, because these impact craters are hot, but impactors also can release or de novo synthesize some gases and substances with global warming potential or global cooling, like aerosols. There is definitely also influence on geochemistry. As I noted, impact mean energy for chemical transformations, and they mean also extraplanetary delivery of chemicals which are not presented on planetary surfaces from the beginning. There is also interesting question, and I will also introduce some experiments focused on this topic, on observation of impacts on exoplanets, because it's one way how to get some knowledge about evolution of early planets, and impacts, of course, belong to, as I noted, to questions we can ask regarding the early planetary evolution. But this is pretty related to much broader question. if we can, for example, or if we will be sometime able to observe and explore early Earth twin and learn something about evolution of early planet from this observation. Yeah. Astronomers can observe stars in different stages of their evolution, and they can learn a lot about their evolution from the observation. We astrochemists, or people dealing with some kind of prebiotic evolution and early planetary evolution, we have nothing. We have some knowledge gap with some indirect evidences, some fossil records, but not real, but only some, for example, zircons. And from that, we have to learn how was the early Earth like. Yeah. So it's very complicated. In case of observation of early planets, we maybe will learn more about the early planetary evolution. Regarding impacts, we can imagine that we can, for example, spectroscopically observe the emission spectra. I will be talking about Meteor spectroscopy. There are plenty of atomic transitions and very specific spectra of meteors. But there is a problem with sensitivity, because with state-of-the-art telescopes, I think that it's impossible, I would say impossible, to observe even very deep impact of a very large body to some planetary atmosphere. Yeah. Surface of the target. Of course, you can observe hot spots or maybe the relief, but observation of surface of some exoplanet, it's sci-fi. Maybe we will never observe surface of exoplanet by some, I don't know, interferometric technique or something. I don't know. Yeah. And then we have absorption spectra, classical transition spectroscopy. And maybe this is the key. And we explore this also in our laboratory, because you have original atmosphere. Then you have some energy and some delivery of substances from extraplanetary space. And then you can maybe observe some markers, so molecules pretty associated with impacts. It's my dream. But more likely you will observe some, let's say, disequilibria caused by impacts in composition of planetary atmosphere. Yeah. It means ratio of some typical chemical substances, like I will show you acetylene, hydrogen cyanide, CS2, OCS, and such stuff. So let's skip to laboratory experiments and simulation of impact. As an introduction, I would like to summarize that we have also a few observations of impacts in the history of Earth, or in history of space observation. We can learn something from Tunguska event. Recently, I have noticed a lot of papers regarding great Chicxulub impact event, regarding, for example, acidic rains after the impact. It means the reprocessing of the atmosphere, by the way, because acidic rains are caused by synthesis of nitrogen oxides by impact plasma. So this is the reprocessing, and the same effect was observed in Tunguska impact site. Yeah. So we can learn a lot about physics and chemistry. Shoemaker-Levy impact recorded on Jupiter. It was a comet, and it is also really specific, because the astronomers observed delivery of a lot of sulfur-containing substances. I was talking about OCS and CS2, and these could be used as impact markers. I will show you this as our experimental result, because they are synthesized de novo, but they also can be delivered by impacting bodies. And then we have laboratory experiments. But here is a problem because all these experimental setups represent only an approach, yeah, including lasers, of course. Yeah. First, what is used to study impact chemistry, a shock tube. Very nice system for exploration of some reaction rates of single, very well-defined reactions, but only appropriate for the gas phase. So, and also they are limited in temperature because in impact you can have temperature 10,000, 20,000 Kelvin. So the shock tube is limited in its performance. Then you have hypersonic guns or supersonic guns. There is a problem with, first of all, speed of projectile you can shoot because it's up to 10 kilometers per second. Usually it's about 7 or 8. And the lowest velocity of a meteoroid coming from space is 10 kilometers per second. So they are slower. And there is maybe another more important issue. They are not much appropriate for studying chemical transformations because you shoot projectile through some tunnel to some target and how you would like to study chemical transformation of some mixtures, yeah, liquids, solids, gas phase. That's problem, yeah. And the third approach are lasers. Here is a limitation that lasers usually produce higher electron density than what is exhibited or observed in meteor plasma. But they have advantage of similar conditions regarding the temperature, 10,000 to 20,000 Kelvin. And also me, as a chemist, I really like that I can close my system to well-defined vacuum-sealed cell. I can shoot inside by a laser. I produce plasma inside, and I can nicely study chemical transformations taking place inside without any interaction with electrodes, with projectile, with the diaphragm in the case of shock tube, and I can mix almost everything. Yeah, so solids, liquids, and also gas phase. So we use tabletop lasers, but also large Hall laser located in Prague. This laser is called Asterix, and you can see that it's pretty big laser. It's one great hole, and there is also one hole beneath with capacitors, and these tubes produce the laser light.
Just to say, this is one laser, yeah? I was standing there and I thought this is several, but it's one.
Yes, it's one. The initiator is here. It's a small laser, and it shoots the laser beam through these tubes. There are tubes producing laser radiation, and there are tubes for, how to say in English? It's like tailoring of the laser radiation because there are reflections and so on. So it's for focusing and so on. Yeah. I will show you how the laser works. And let's skip to experimental arrangements. First, how this laser operates. It's kind of not real chemical laser because chemical laser produces laser light with chemical reaction. Here it is kind of chemical reaction, but you have recuperation of this compound. By flash photolysis, it produces iodine in excited state, and this is forbidden transition. So by hit by another photon, it emits two photons like classical laser. And so you have inversion of population because it cannot just simply shine light from this forbidden transition. And then after the excitation, it reacts back and you recreate the starting compound. And this laser is able to shoot laser pulses up to 1000 joules every 30 minutes. So the repetition rate is not high, but the energy focused in one laser shot is pretty high, 1000 times or 2000 times higher than you can reach with simple tabletop lasers in your laboratory, but with low repetition rate. I will show you maybe then again two kinds of cells. It's a 20-liter cell filled with studied atmosphere. So you create a laser spark inside the size of grapefruit. And here is smaller cell, and this can be filled with solid, liquid, or mixed sample. And we create usually a laser spark in gas medium above. So the surface filled with liquid or solid is hit by the expanding laser plasma because it filled completely the inner volume of the cell. You have to focus the laser light by lens, because the laser produces the laser beam of the diameter like this, so about 20-30 centimeters. And depending on which tube you use as the final laser tube producing the laser radiation, it depends also on power of the laser light you need. And then if you focus the laser beam, it reaches the limit of radiation density for the dielectric breakdown, and it just burns the air and or gas media, and it expands. So it produces so-called laser-induced dielectric breakdown. This is the laser spark. Then we analyze the mixtures using Fourier transform spectroscopy. It's the first technique for examination of the composition of gas phase after the several laser shots. The advantage is that it's very nice for bulk analysis. You can record absorption spectra of particular molecules. They are fingerprints. You can also quantify using absorption coefficients. So it's very nice for the first examination. And we also compare these results with small tabletop lasers. We call it mini pulse or mini Asterix. This experimental setup. And in this experimental setup, we use small tabletop neodymium YAG laser. The advantage of this setup is that it does not produce so large laser sparks, of course, but with very limited energy, about half joule. But you can deposit to your system much more energy than using this large laser, because as I noted, the repetition rate here is 30 minutes. With 1000 joules. Here the repetition rate is 1 hertz with 0.5 joules. Yeah. So for, let's say, complete transformation of certain media, it's a really appropriate system. For the analysis, we use also this multipass cell. White cell is equipped with mirrors, and you in this way extend the optical path, and you have then a higher detection limit. After the laser experiments with some media or mixtures related to prebiotic chemistry. We performed detection of prebiotic substances, sugars, amino acids, and nucleobases by GCMS chromatography. So they are derivatized using this silylation agent. It's because it's gas chromatography and you need to volatilize your sample. Nucleobases are very badly smelling crystalline compounds. Yeah. So in order to inject them to gas phase, gas chromatograph, you need to create the vapors from that. So it's this chemical trick. Finally, I will show you at the end of the presentation also the interaction experiments with samples of meteorites. We use this large cell which could be fully evacuated, and then the laser radiation is focused on the surface, and we record emission spectra using high resolution spectral spectrometer, but also spectral cameras used by astronomers for meteor observation, and under laboratory conditions you can explore the physical parameters of the plasma and their spectra. So these are target interaction experiments. And finally, we combine our results with theory also. In order to understand the chemical transformations, we outline the chemical spider. I will show you some of them. And theoreticians then recalculate the most plausible chemical pathways in plasma. We collaborate with these three guys, Giuseppe Casone, Francea, and Marco Saita from University Sorbonne. And Franz and Giuseppe come from this Institute of Chemistry of Italian Academy of Sciences in Messina. You can see how these guys work usually. So they go to the beach, they open the laptop. Then they go for ice cream. They return to laptop, they take the result and adjust and send it again. And I smell chemicals in my laboratory in meantime. We collaborate also with Paul Rimmer from the University, or we have collaborated with Paul Rimmer, and we are still collaborating from the University of Cambridge. He does not perform quantum chemical calculations, but as my colleagues here from Graz, Helmut and Peter, he is skilled with the model of planetary atmospheres and planetary chemistry models. And then he introduces our results to his chemical networks, and we can guess, for example, if we produce certain molecule in impact plasma, does it survive for how long in the planetary atmosphere? What are the results of this molecule chemical transformation, and so on. Yeah. So this is introduced to his models. We also in our laboratory perform simulation of plasma chemistry regarding the kinetics of plasma and examination of physical parameters of plasma. This is important to understand how related are plasma conditions to real impact event, where are the limits, as I noted, in electron density, and where are the similarities regarding, for example, plasma density and temperature. So this is in order to understand, let's say, the initial step of some compound plasma transformation and producing radicals and simple compounds. This is, by the way, model of plasma created in formaldehyde papers. So I would like to, as I noted, introduce several experimental results as pieces of puzzle. We have explored early environment, plasma transformation of atmospheres, reprocessing of impactor, and consequences to early Earth environment. Regarding the origin of life, we have demonstrated the synthesis of prebiotic molecules, but also origin of prebiotic molecules in impact craters, because we also perform some additional experiments related to impact, but not by utilization of lasers, because we would like to put together all pieces of the story. So it means the transformation of environment, prebiotic synthesis, but then what is also going on such world exposed to impact. And also we have somehow explored the delivery of some prebiotic substances. And finally, I will be talking also about observation of meteors and impacts. Meteors are also key for understanding the impact chemistry and chemistry. So that's why we are also collaborating with meteor observers, and we are trying to somehow study also meteor spectra. It regards physics and spectra, as I noted, and identification of impact markers in planetary atmospheres. And let's skip to origin of life. We are ending here with prebiotic molecules. We cannot, with our, let's say, laboratory equipment and scientific focus, care too much about this miracle, how the mixture of prebiotic molecules can produce life, for example, established on ribonucleic acid. Yeah. So this is what we explore, these initial steps. But we are really interested in synthesis of all building blocks of life, all prebiotic molecules like canonical nucleobases, sugars, amino acids, and so on. Because what is interesting regarding the impact plasma or simulation of impact plasma by lasers, it represents also the impact, as I noted, regarding all the phases and different mixtures of molecules. I can compare it to explosion in a drugstore. And in this explosion, we would like to observe all the products. So it means, for example, all the canonical nucleobases, important sugars, and so on. So for us, important experiments or important experimental result is if we create in this system, we explore, we study using the laser simulation of impacts. If we produce all the nucleobases and sugars in one pot. I would like, if I start with some kind of historical experiments. These experiments started around 2000, so 24 years ago, by synthesis or experiments focused on synthesis of basic amino acids. But I would like just to note that the Prague Asterix laser system is a bit older. It comes from Garching, Max Planck Institute, because they sold it for 15 minutes. Okay. They sold it for a symbolical 1 mark to the Czech Republic, because it was old laser in that time. And we built a new building. People just collected all the parts, reconstructed the laser, and it's now used for chemical experiments and plasma physics and plasmochemistry. In Garching, they used it for, as I know, for experiments with fusion. Yeah. Okay. Regarding the history, we started in 2004 with investigation of synthesis of amino acids. Then we skipped to some deeper exploration of plasmochemistry. And 12 years ago, we have demonstrated the synthesis of nucleobases in impact plasma. This is one unified scenario reconstructed from many experiments and many studies. And here I would like to show you just that there is very interesting impact chemistry initiated directly by the plasma. We demonstrated the synthesis of all these basic substances from formamide, but also from other starting compounds initiated by plasma. And we also detected the major intermediates in this chemistry. And this scenario was completely reconstructed by quantum chemical calculations and then published. So this is the direct action of impact plasma. But there is also post-impact chemistry, as I noted, taking place in the impact crater, and it's just supported or it's just supported by heat. Heat is the source of energy. And we also explored this, but we explored different catalysts or surfaces. And some of them are more friendly for prebiotic synthesis and its yield. Some even block, and some don't have effect. Yeah. We, for example, also tested some spontaneous reactions, but also action of radioactivity by irradiation of these samples in gamma cell. Yeah. So this is also a complete scenario of post-impact chemistry. My opinion is that, however, I am laser guy, and I spent maybe 1/2 of my career by these laser experiments, only by these laser experiments. I think that maybe this post-impact chemistry is more important for prebiotic synthesis, because this can take place in seconds. Here you have, for example, 300 million years, like in case of Gale, where they assume that the hydrothermal activity, this site was hydrothermally active by post-impact heat for these 300 million years. So this is maybe really important, these transformations. We have also demonstrated that all the nucleobases can be created from hydrogen cyanide. I was talking about formamide, which is favorite molecules for some groups, and hydrogen cyanide is favorite starting prebiotic compound for other groups. I mean that these two chemistries combine, and it can be easily demonstrated by these laser experiments, because from hydrogen cyanide, but formamide also, you can create all the canonical nucleobases. So both molecules can exhibit one-hot chemistry. Very interesting. There are also other precursors. We have spoken today with my colleagues about formaldehyde. Formaldehyde was also exposed in our laboratory to laser sparks, and it produced sugars, and it produced also formamide. And from formamide, we have noticed that also, again, all the nucleobases are created. Formaldehyde is pretty interesting because, for example, the concentration of formaldehyde in interstellar medium or interplanetary and interstellar objects is even higher than for formamide. So it would be very interesting starting prebiotic compound. This just demonstrates the formation of basic sugars from formaldehyde. Maybe as a chemist maybe you already heard about so-called unparalleled problem, that formaldehyde cannot create glycolaldehyde during this dimerization, this reaction step. But we have demonstrated that this reaction step could take place by initiation with laser spark, and then there is autocatalytic cycle, and it could produce all the sugars from formaldehyde. So this is maybe interesting contribution of impacts, very crucial, let's say, because it could produce in high energetic environment this compound, and then there is a autocatalytic cycle of sugar creation. Another interesting result was achieved just by exploration of post-impact chemistry. My colleague from the Mendel University in Brno is very interested in synthesis of quantum dots. So we tried some prebiotic synthesis initiated only by heat in laboratory, and there are very high yields if you put quantum dots to formamide and heat it. So yield can be increased several hundred times for some nucleobases. And also, there is very interesting property of quantum dots. These guys from the Mendel University demonstrated that these dots can behave like protoenzymes. They demonstrated peroxidase activity, for example, as an example of this activity. So maybe the initiation of some, let's say, metabolism and increasing of yield of prebiotic synthesis was related to quantum dots. And these dots are related to impacts because, as you know, meteorites are rich in heavy metals. So in some impact place, if you have tiles and just UV radiation, you can easily produce these quantum dots, which is really interesting. It's not really hard to synthesize them. So this is just to summarize this chemistry. We have different routes of prebiotic synthesis initiated by impact and also post-impact chemistry, and then it goes through miracle to complex work. Let's skip to early environment. We have explored, for example, in our laboratory sample of the Ryugu asteroid, and we discovered a lot of very interesting organic compounds. And using electron microscopy, we have mapped how organic compound is are presented in the asteroid matter. And it's interesting because there is phyllosilicate grain. Phyllosilicate is created by water alteration, which is really interesting in case for asteroid. And then they exhibit very likely catalytic properties because we observed also increasing of yield if you use in prebiotic synthesis, if you use phyllosilicates in your experiments, and they produce organic substances and they cover these original phyllosilicate grains. So this is related to exogenous delivery of organic compounds. Reprocessing of hydrogen cyanide, we have also explored simple chemistry of this molecule, and there is also debate about the delivery and the de novo synthesis of hydrogen cyanide. And here we achieved very interesting experimental results, must be evaluated in future and discussed, because we observed almost the same decomposition rate, like rate of de novo synthesis of hydrogen cyanide. And the fluxes from interplanetary space and also from the synthesis are then comparable with the production rate, with the decomposition rate, sorry. So this must be very carefully evaluated because some people, and I was also believe in that early environment was rich in hydrogen cyanide, but we must be careful about how rich, if the decomposition rate is so high. Regarding the nitrogen oxide, its story, we also discussed with Helmut Lammer. The origin of N2O on early Earth. Again, it's produced, but according to our results, this gas has warming potential, but the production rate wasn't enough to create a global warming effect on early Earth. Yeah. So again, regarding impacts, the real numbers coming from experiments can somehow point also the limits of impacts and their contribution to early Earth environment. I was talking also about argon and xenon ratio. We performed the experiments in our laboratory regarding how easy it can be ionized xenon and argon, because there were no experimental data. And my colleagues from Cambridge, they put it in the global model of early Mars atmosphere. And this is important because argon and xenon, after ionization, can escape around magnetic field, the atmosphere of Mars or early Earth. And their model has shown that the depletion of xenon to argon is in agreement with early impact flux of 10 to 16 grams per year of the impacting interplanetary bodies, which is really interesting because it's in a good agreement with what is expected for Mars and also early Earth. And finally, observation of meteors. I was talking about possibility to observe meteor spectra on exoplanets. It's sci-fi, but definitely meteor spectra are crucial for some analysis of meteor and impact physics. And also we have performed some experiments with reprocessing of several atmosphere types. And we evaluated the possibility to detect the molecules produced by impact and their disequilibria in transition spectra of exoplanets. This is the basic idea. So you have transition spectroscopy, and if you take a yield from our experiments, it means joules needed for production of molecule of some product of plasmochemistry, then you can put it to Argo model, and by simulation of transition spectra, you can estimate if there are deviations from some equilibrium chemistry. In case of early methane-rich atmospheres, we have identified that you can, for example, observe much higher concentration of acetylene and also hydrogen cyanide. And regarding the chemistry of sulfur compounds, you can observe OCS, CS2, or disequilibrium between OCS and CO2 in impact exposed environment. And the meteor spectra, finally, as I noted, we are interested in meteor spectroscopy. We have simulated by ablation meteor spectra. It was important for astronomers because under control conditions, you can produce these spectra. You can fit, and you can then, using your model, estimate the elemental composition of meteors. It's a little bit tricky because it's not like in laser-induced breakdown spectroscopy that you measure something in laboratory and you have elemental composition. There are a lot of but people dealing with LIBS analysis can tell you stories about precision of such an analysis. And then imagine that you have very complicated phenomenon with envelopes of electron densities and temperatures, and you estimate the composition of a meteoroid, of body traveling through atmosphere based on spectra shined from the meteoric event. It's really tricky, and I would tell you that these laboratory experiments can help a lot in this elemental analysis based on these emission spectra. And of course, this is super important because for free, you have samples from different parts of solar system, and you can just gather the elemental composition of bodies if you know the trajectory, of course. Yeah. So this is the meteor physics, and when we started with these explorations, we identified that the UV region, which cannot be observed from ground-based observatories, is actually very rich in a lot of transitions associated with elemental composition of interplanetary matter. And we started thinking about possibility to launch some kind of CubeSat mission to observe meteors from orbit of Earth. We have outlined a project focused on developing of such hyperspectral camera able to provide or record the meteor spectra on board the satellite in UV region. And we also outlined the feasibility study of mission of tandem of two satellites able to observe meteor spectra, and also because you have observation from 2 points to record data for trajectory calculation. It means possibility to calculate source in the solar system. This mission was also equipped with advanced orbit wrapped bus spectrometer, miniaturized device able to analyze interplanetary particles. So during the meteor shower, it's very nice because you can have meteor spectra, elemental composition, and very precise analysis provided by mass spectrometry. And there was also a radio antenna for recording the meteor plasma radio signal in order to learn a lot about meteor physics. This is just a few shots of the meteor camera we are now developing in our laboratory. We call it Hyperspect. And we used ablation spectra for testing the performance of this camera under laboratory conditions. Yes, it's very end. So we are coming back to this LIPS because it's for us also important to evaluate how this optical system and electronic system of camera works. And finally, we also will launch this camera on board the stratospheric balloon in observed Gemini meteor shower this winter in middle of December. And this is just the conclusion. We can skip it. I will share the presentation with you, so you can read it. And I thank you for the attention.